Okay, you could say what I've been interested in, or what my sort of thinking is drawn to in thinking about statistics, is the pragmatics of statistics. So I'm not a statistician, but I'm a cognitive psychologist, and I wanted a sort of a way of doing statistics that fitted what I wanted to do, and what it often was to test theories. So how could I test theories severely? So I've been motivated by Popper. Popper, in fact, when I was in the sixth form, my headmaster gave me a little book on Popper to read by McGee, and ever since then I've taken a Popperian view of science, which might have been partly because my mother was a Scientologist, and then Popper made sense to me of, why is Scientology not a science? Okay, that makes sense. So I find myself wanting to test theories, and if you're going to test theories, you want to do it severely, so how do you go about doing this? So Popper said a severe test means you make the theory stick its neck out. And one way he put this in 1963 was what you want is the predicted outcome is highly likely given the theory, and highly unlikely given the rest of background knowledge. Incidentally, many of the ideas I'm talking about is in this book chapter. But that way of putting a severe test makes it sound conceptually similar to a Bayes factor in some way, because what a Bayes factor is the data is highly likely given H1. Well, it's the probability of the data given H1, divided by the probability of the data, say, given H0. So one way of saying what a severe test is, you've set up an experiment that's a severe test of your theory, if it could generate an extreme Bayes factor. In other words, do you have enough subjects and items and so on, that you could get a Bayes factor that's very high, given H1 is true, or very low, given H0 is true, for Bayes factor this way around. But that would only be a severe test of the theory if the way you had modelled H1 followed from the theory. In other words, is your model of H1 a model of the predictions of the theory? So if you wanted to use Bayes factors to test theories, which I do, then I need to make sure that my model of H1 is derived from the theory in some simple way or empirically motivated way, using assumptions which are well tested or simple. Now, there are going to be different ways of modelling the predictions of a theory that satisfy this. In other words, there's a sort of a one-to-many relationship between the theory and your models of H1. Now, I'll call this a model of H1 rather than a prior. I mean, most people call it a prior, but there's another sense of prior, namely if you're trying to get estimates from your data of mean differences or slopes or whatever, you might have a prior. But that's a different sort of prior, because your model of H1 in the Bayes factor has a function of representing the predictions of the theory if you're in the business of theory testing. But when you have a prior for your data to get your estimate of your mean or your slope or whatever, what you want is an accurate estimate of the mean or the slope. So, for example, if the mean can't, you might have very good reasons for saying the mean can't go beyond a certain value. You reflect that in your prior to make sure that the mean is constrained within certain values that it should be in. And of course, there's another meaning of prior, which is your prior odds in H1 versus H0, which would multiply by your Bayes factor. So there's three meanings of prior at play here when you use Bayes factor. I just sort of mentioned all this because I find people often confuse them. It's often critics of Bayes who mix these things up in order they might, for example, think you're talking about prior odds and say that's very subjective, how much I believe in subliminal perception, and that counts against using Bayes factors, when it doesn't, because when you use a Bayes factor, what you're trying to do if you're testing theories is representing the predictions of your theory. But I see other people confusing these things as well. Now, I want to illustrate this because another thing is there are other ways of using Bayes factors in which you're not trying to test theories, it seems to me. And so your model of H1 does something else. For example, it could reflect what someone truly believes if they look within themselves about the probability distribution of some parameter. But when you do that, you're not really in the business of testing theories. So I just want to illustrate this with a couple of examples. So I'm going to talk about not Aphantasia, in other words, Aphantasia. Okay, I'm going to keep my day job. So let me tell you a particular sort of substantial question. There's something called phenomenological control, which is the ability of people, 90% of people, they can construct subjective experiences that systematically misrepresent reality and do that according to the goals. For example, I'll do it right now. I imagine my hands are like magnets. And I feel a force pulling my hands together. And actually, I really feel the force pulling my hands together. So I've systematically misrepresented reality in a way that's subjectively compelling. That's phenomenological control. I've controlled my phenomenology. Now, does that depend on imagery? And so one question is, would people with aphantasia show this ability? Aphantasia being the condition in which you experience zero vividness of imagery. You close your eyes and think of an apple. There's nothing there. You have a concept of an apple, but you don't see an apple. Well, Julia Cabai, who's a PhD student at Sussex, not my PhD student, she regressed people's phenomenological control abilities against the vividness of their imagery, and indeed there is some slope there. So there is some relationship between your ability to do this sort of things, which an example of this you might know about phenomenological control is, for example, responding to hypnotic suggestions. But it's more general than that. People construct these experiences in many situations. So there's some relationship. So maybe we could have a hypothesis that people with aphantasia, if you contacted aphantasic groups, which are internet groups like this, recruited them and measured their phenomenological control, you would find that it was low. These aphantasics with no visual imagery. Indeed, Julia did this, and she got a difference in phenomenological control of 1.39 units. It was, you do a Bayes factor on this, JZS, scale factor 0.7, it's enormous, and you say, well, that's fantastic. Fantastic. We predicted that the phenomenological control would be lower in the aphantasics, and it was. And its Bayes factor is so huge, obviously it doesn't matter what your model of H1 is, what your prior is. It's going to show evidence, whatever you do. But hang on a minute. This slope we got, yes, it was there, but the intercept we get with zero vividness of imagery on the imagery scale, the intercept for phenomenological control is actually reasonably high. You only drop a little bit, going from average imagery to zero vividness of imagery. You drop half a rating unit. But with these aphantasics, they dropped more or less 1.5 rating units. So is this hypothesis really confirmed that people with aphantasia have low phenomenological control scores because they do not have imagery? Is that what's going on here? Well, one thing that happened when Julia ran the study is she got angry messages from the aphantasics saying, you bastards, you know we don't have good imagery, and here you are giving us imagination exercises. So there's another hypothesis that there's demand characteristics going on. The aphantasics have an identity of being aphantasics. Here are some experimenters giving them imagery, imagination exercise, and damned if they're going to be any good at this. So let's have two hypotheses. One is the difference between aphantasics and normal people is due to the lack of imagery, and we from the intercept of the regression equation we had before, we would show that the effect size there should be about half a unit. Now, when it comes to demand characteristics that say we don't really know how much it could work, but demand characteristics could reduce a phenomenological control anywhere from the average of normal people down to 0. So we just put a uniform from there. So the different theories make different predictions that we model in different ways to reflect the different predictions. So one thing I want to point out about this is in rocket science. This is fuzzy-wuzzy consciousness science, but we can still make predictions in raw units of effect sizes when we think about it. And in some ways you could say what I've spent my career thinking about statistics doing is thinking about how one does that. And indeed, if you use Bay factor comparing those two models, you get almost strong evidence for the demand characteristics rather than the imagery hypothesis. So we disconfirm the hypothesis that we started with. So in order to really test the hypothesis we were talking about, we needed to think about what is it are we really predicting? What about the scientific context and what we know constrains the effect size in raw units, and I always like to think in raw units. So the next point I want to make is if your theory predicted an effect, non-significance does not count against it. I'm not sure you're with me there. But I also want to say no approach that does not determine scientifically relevant effect sizes does either. So I put in that category 3 square root n p as well. And, BIC, AIC, any of these things. And the reason for that is evidence for no effect is always relative to the model of what size effect there could be. That's sort of obvious. And when I teach this, I sort of motivate that thought. I ask, is there an animal in the room now? Non-human animal. Well, it depends what I'm talking about. If I'm talking about a rhino, you just have a little glance around and you say, I've got really good evidence there's not a rhino in the room now. But if I say, well, you know, what I'm talking about could be an ant, you say, well, I don't know. I need better evidence. I need to get down and, just as I was demonstrating just now, and have a proper look at the floor. So you can't tell if there's any evidence for something not being there until you know how big the thing is that you're looking for. Are you a rhinologist or an antologist? Well, rhinologists investigate noses, but anyway. So, to illustrate that, there was this paper that's been reasonably influential in the sort of the subliminal type literature by Pesiglione, saying they got subliminal instrumental conditioning. And the way these things often work is you show that there's some awareness check that was non-significant, which was here, deep non-significant, T bit less than 0.5. But then, even though the stimuli showed is subliminal, it is argued, because you've got non-significance, there is some other effect that shows that the information is processed. So there's a learning effect, D prime is 0.7 or significant. Now you could say, well, that's just p-values, so what do we care about that? Well, you could do a JZS sort of default base factor, and you get a base factor 0.26, and you say, well, you know, less than a third is moderate evidence. So yeah, they've got moderate evidence that they did not consciously see the stimuli. Well, what Lena Scorer did, another PhD student from University of Sussex, is to run exactly the same experiment, but with a longer exposure, so the perception was conscious. We can all agree the perception was conscious. And then you get a certain learning D prime and a certain awareness D prime. Both of these were highly significant base factors. So then you say, on the theory that the learning would only occur because subjects who relied on the subjects being consciously aware of the stimuli, then if you had zero awareness of the stimuli, the learning should go to zero. That's the theory that this is all based on conscious knowledge. Well, the simplest way of representing that theory would be to say they go down to zero in a linear fashion, or at least linear is a good enough approximation. Well, then we can look at the level of learning that Pesiglione got, and it was 0.7. And then you can read off roughly what you predict for the amount of awareness. Now, you see, when you think about things this way, rather than doing defaults or just looking at p-values and so on, it behaves in a scientifically reasonable way, in that the more learning that was shown, the bigger the awareness you expect, which is how it should be. So in other words, the sort of effect that you're looking for is now defined in raw units. And what that means is you can't get away with saying just having a few trials and getting a non-significant result or a high or a default Bayes factor that's very low, because noise now can't be in your favour. If you're having a noisy measure, it's going to show up as a Bayes factor that's close to 1. Yeah, 5 minutes, almost there. So now if we do a Bayes factor based on this effect size as a scale factor, and I'll do a sort of a half normal as a reasonable way of representing this, we get something that's fairly close to 1 and pretty much non-evidential. How I often represent this in my papers, I give something called a robustness region, where I give all the scale factors that would lead to the same conclusion, in this case non-evidential. Say you can specify a threshold with a threshold of 3. And all the scale factors that do that between 0 and 0.83. And that shows how robust the conclusion is with respect to our scientific measures. And that shows us really pretty robust, because the learning D prime is 0.7, and this is robust up until more than the learning D prime. So I regard that conclusion as pretty robust. So that illustrates a couple of little examples to illustrate, I think. If we're in the business of wanting to test theories, we should be motivating our model of H1, I reckon, in raw units, not Cohen's D, not standardized units. We should be interested in raw effect sizes. Now, Mayo has been going around, Deborah Mayo, saying if you want to do severe testing, the one thing you shouldn't do is Bayes and Bayes factors, because they give no protection to P hacking or B hacking. And I've always been a bit bemused by this, because I didn't quite understand why exactly she thinks this. Because if you play around with exclusion criteria, coding criteria, and so on, you P hack or B hack, and you push your mean difference about by whatever hacking procedure you want to do that, basically you're changing the likelihood function, because the probability of getting a certain mean difference is now more equal for given H0 as given H1, because you can push it about. So to use Bayes factors using standard likelihood functions, we need to protect against P hacking, B hacking, and all this sort of cherry picking. Then she says, but the likelihood, okay, I don't know if she says okay, but she says the likelihood for evidence allows optional stopping, and the answer is right. And EJ has a very good paper on that this is exactly what we want evidence to do. Evidence accumulates. And even a frequentist, when they're learning a foreign language, will not give themselves 4 weeks to learn the meaning of this word, and after that, nope, I'm collecting no more evidence. We never do that. And in a scientific context, if you can't keep on accumulating evidence, we can't do things like meta-analyses, and in the end, we can't severely test theories. So this has been my argument for a way of thinking about using Bayes factors for severe theory testing. And when I think about what's the philosophy, the Bayesian philosophy behind it, well, I don't think it really is a Bayesian philosophy. I think it was Popper's philosophy, at least when you think about the people he immediately inspired, is often called critical rationalism. You could put it like this: test the predictions of each theory as that theory applies in each scientific context. So there should be reasons intrinsic to the scientific context for defining the model of H1. Why did I pick that scale factor? What I'd like to be able to do is to point to some. It's not that I just pulled it out of me and said, I think that feels good. I can point to some source. The number here, I got it from here. That's where I got it from. But that contrasts, say, I sort of think of it as sitting, straddling the line between objective Bayes. We use a default Bayes factor in every case. But that makes the assumption that every theory makes the same prediction in every context, given it predicts an effect. And that's not quite what I want to do. On the other hand, subjective Bayes, you say probabilities are purely personal. So you have to ask experts to generate models of H1. How big an effect do you think you're going to get in this situation? I know what. We'll ask Maria, because she works in the field, and we'll elicit some prior from her. Then the predictions of scientific theory can be different for different people, depending on how they feel. And that sort of, to me, violates my Popperian intuitions of objective knowledge, that we should have predictions following from theories for simple and well-tested reasons that we can argue about, talk about. And that's it. Thanks very much.
Okay, so thanks very much. So anyone for questions or comments? So just one, okay, so just one question on this. Oh, sorry, why don't you?
I have a question more in the practical side because usually we don't have a sense of the effect size that we are looking for because we don't have previous evidence of that give what is an effect size and how to proceed from there. And I was wondering what it would be your suggestion.
Yeah, so the question is, I mean, in many experiments, there's no relevant... I mean, one thing you can do is if there's relevant previous experiments, you have an idea of the sort of effect size you get, but you're not always in that situation. You might think your experiment is different in some crucial way. So I've written a few papers of how I do that. So I publish a number of papers a year in my areas of substantial research, and I always use the approach I'm talking about, and I have done for, at least 2015. If you notice, say, in the subliminal perception experiment, what we did was we ran a sort of called a pilot or a norming experiment. It wasn't to get the effect size, it wasn't to get another estimate of the very effect size we're doing. It was to get an estimate of something that, according to the theory we were going to test, is relevant to predicting the effect size that we're talking about. There might be constraints within your data. For example, theory testing might be saying whatever the effect is, it must be smaller than shown in some other group or condition. So then you can run this other condition, and that sets a norm by which you say, well, whatever it is, it's got to be in this interval here. That's what I call the room to move heuristic. If you look at my website, I have a number of papers where I go through a number of heuristics like this. Now, I think if you really had no idea of what the effect size is you're looking for, you just can't get a handle on that. I wonder if we should be using Bayes factors. Maybe we should just be estimating them. Because how can we be testing a theory if we don't know what the size of the thing is that we're looking for?
One theory is that instead of just testing some H1, we try to find the best possible alternative. Theory to zero and then test that against H0.
Sorry, I missed that.
So the approach we described is to find a very good alternative to H0 and test that against H0 instead of just arbitrary testing for.
Yeah, so you're saying, well, what am I suggesting? Yeah, you don't take an arbitrary H1. But what you want to think about is, what is it that I'm really interested in here? What is it I'm trying to test? And what follows from that? What are the ways of representing the predictions of that theory? In other words, what's an interesting theory that I'm trying to test? I actually think that question, at least I can speak for psychology, a lot of fields of psychology, doesn't come naturally to people. A lot of people don't actually think about what is a general interesting theory here that I'm trying to test. So as an editor, for example, I found myself asking authors, or an author, well, what's your theory here? And then they come back, it's theoretically relevant because of this, and I say, yes, but what's your theory? And sometimes in the end I've had to suggest a theory, just because people don't think that way normally. And I don't know if it's just me, but what I found interesting about science is the general interesting theories that have survived severe tests. So I find myself always wanting to think, what is some simple, interesting theory that could be at stake here. And then what we're trying to do is to think about how can we represent the predictions of that.
Thanks for your talk, Sultan. I
Thanks.
think it's a really interesting approach, and I do think actually that when you showed the example where you had a base factor of 0.26 and it went to 0.65, I actually think the 0.26 adds some useful information there. That's kind of a point of reference or something like, this is what we do if we went about it without inserting extra knowledge, and now we insert the extra knowledge and we get this outcome you can argue is more informative. But the question I wanted to ask is, so I've read Popper, and I actually, so I like your work, but I don't like Popper's work at all. And I think that if Popper were in the audience, that he would actually be highly critical of this, because he didn't like Bayesianism at all.
No, Popper hated Bayes, seemed with every fibre of his being, but he never talked about Bayes factors. I mean, he might have had one footnote to Lindley or something. To Jeffreys. But his criticism of Bayes was all about, are we really interested in the posterior probability of hypotheses? But when you think about Bayes factors, I think it's very Popperian. I mean, I agree, I'm not saying Popper would agree with me, he'd probably have fits, but...
Well, I have one thing to say about that. So Popper at some point thought, like, okay, instead of being interested just in falsification, it would be nice to have a measure for confirming the strength of the theory. And then what he ended up proposing, he didn't know this, was actually a Bayes factor.
Well, exactly. I mean, because that's sort of what I started with. So confirming the theory is you give a severe test and passes the test. So there's a high probability of the outcome given the theory, and a low probability given the rest of the background knowledge, which is what we started with, which is basically a Bayes factor. Exactly. That is his measure of corroboration. So that's why I think it is actually very Popperian.
So I had a question, which is, so to try and understand your example there, so if I understood, you have three hypotheses, which we're calling H0, H1 and H2. And H0 is there's nothing going on in terms of the response. H1 is it's determined by phenomenological control, and H2 it's due to it's the
demand characteristics.
The demand characteristics.
Yeah.
And you found there you are. So you found the H1 was favoured by the Bayes factor over H0, but H2 was favoured over H1.
Yeah.
And so I'm wondering, a common approach, certainly in social science, would be to say, okay, we also consider the possibility that both imagery and demand characteristics are operational, and then, and then you ask, is that better than H2? So why didn't you do that? It seems, for example, in social science, if you've got age and sex, and you've got something else of interest for explaining like how jittery are you as a function of how much coffee you've drunk. Well, maybe age and sex will have a bigger effect than coffee, but coffee might still have an additional effect. So
I'm not quite in a regression situation where I can simply put in these as different... For example, demand characteristics is a theory I have, but I don't have a measure of demand characteristics put in an equation. Surely this is operational because we have shown Julie has shown in other data that imagery does have an effect in phenomenological control, and so I'm sure that is operational, but the effect is small. So I think that effect must be operating there. Why wouldn't it be? Sure, I agree, it is operating there, but the effect we're getting is just too big. In fact, I sort of thought of this example because of an example that James talked about, where he talked about you might be interested in parapsychology, but the effect you get in a parapsychology experiment is just too big to be believable. So the data actually convinces you that parapsychology is not at work here. So it was that James example that was sort of in the back of my mind when I thought of this.
Is that the imagery effect, you're rejecting the imagery hypothesis based on this Bayes factor for H2 versus H1?
Yes, you could say the hypothesis that it's only because they do not have imagery. So we're rejecting the hypothesis that it's the one that it's the one cause.
How about the hypothesis that it's both demand?
Yeah, no, we don't reject that one. I wouldn't reject that one.
You wouldn't?
No,
and
I
that
wouldn't.
would say imagery is operational. So.
Yes, in fact, I think that's true because of the previous data. Yeah, but it's just a small part of the overall effect.
Okay, but that's, Bayes factors really make some. They don't necessarily involve some kind of threshold about what's big or what's small. It's
No.
about reality of an effect.
Yeah, so I just didn't test that joint hypothesis. Yeah.
But and is that like in psychology? Because in social science we would always look at the joint.
Well, you could, except you can't in this case.
Oh,
This is not a regression situation. I can't put both in the equation. So you can only test a parameter if you have the parameter there to test. So that's why I couldn't do it in this case.
Okay. Well, I think we thanks so much again.
Cheers.
Okay, so thanks to all three speakers for really fascinating talks.